Hello everybody, it's Mr. Ray here again. We're going to continue on with our grade 12 data management course. So we're in the first unit, which is called Permutations and Combinations. It's, again, like I said last time, it's just a fancy way of talking about complex methods of counting things. How many ways can we do things, or how many ways can we select things? Most of the questions at the end of the chapter, we'll start with the phrase "how many ways," or how many different ways can we do something or choose something. Okay, so the first lesson we looked at some basic counting. We're going to turn up the heat a little bit. Today's lesson is called Factorials and Permutations, and you can see the word permutations. That's actually the first part of the actual name of the unit. So the permutations is a key part of what we're going to be learning overall in this unit. Okay, factorials is actually, it's a mathematical function that's going to help us with permutations and with other methods of counting as we proceed. Okay, so in order to kind of understand what permutations are, I'll just do a very straightforward example. Say you had 5 members of your family, I guess mother, father, sister, brother, and baby, or something like that, and you wanted to have a family photo, and you wanted to find out, well, how many ways can we actually position the family members to take a photo, assuming it's a left to right photo. Okay, so if you had 5 family members, and you wanted to start arranging them, a lot of the work examples I'm going to do, I'm going to put like boxes to put basically the position. So for the 5 family members in the photo, I'm going to have 5 positions for the people to be in. Okay, so if you think about, well, how many ways can, how many different people can go in the leftmost position? Well, that's pretty simple. We have 5 family members. Each one of those could be there. So we have 5 possible people to go in there. Now, once we've chosen that person, it's kind of locked in there. And now how many do we have left? We've got 4 left to choose in this second to the left position. So we have 4 people we could choose there, and you can continue the logic as you remove one possible person as you place them. The next position we have 3, 2, and once we get to the very last one, we really don't have a choice. It's just one person left. They have to go there. So we could put it there. So at this point now, if I'm looking for how many ways can we arrange these 5 people in a photo, this is going to be a multiplicative property, the product rule, as we call it. So if you think about it, this is definitely multiplicative because it's a person there and a person there and a person there. It's not or. So just about everything we do with permutations, it's going to be using the and, which means we're going to be multiplying. So basically we take the number of people that we can have in each position and multiply the numbers together. So it's going to be 5 times 4 times 3 times 2 times 1. So that's 20, 60, 120. So that's equal to 120. Possible arrangements of positioning these 5 family members. Okay, so we actually, as you can imagine, as you increase the number here that you're trying to arrange, the numbers are going to get bigger and bigger, obviously, but the math becomes, quite cumbersome. So we actually, this is where we introduce this thing called factorial. So if I want to actually calculate what's the result of 5 times 4 times 3 times 2 times 1, well, that's just, we call that 5 factorial. So The factorial part looks like an exclamation mark. It's very dramatic looking. But you can actually find this button on your calculator. It's on most calculators now. I don't think I've ever seen one that didn't have it. So you just press the press the digit 5, then the factorial button, and the number 120 pops up. Okay, so that's basically what a factorial is, and this arrangement would be called a permutation. Okay, now it's important to get a good understanding of what a permutation is. Permutation means you're arranging things where the order does actually matter. It matters who's in this left position, who's in the middle position. Okay, the order does count. It does matter. Okay, so that's what permutations are. Okay, so if we kind of go into the definitions here, combinatorics, again, that's just the field of math dealing with methods of counting. And then the factorial here, I know this definition's a little dictionary-ish. It's short form of writing a series of multiplications of consecutive numbers. Now, you could only do this with natural numbers, meaning, integers 1 and above. For now, you can't use fractions, negative numbers, decimals. It's always natural numbers. Okay, so this is the official definition, and factorial is n times 1 less than n times 2 less than n, so on and so on, and you get down to times 3 times 2 times 1. Okay, so that fits all possible values of n, and we read this as n factorial, or if it was 5, it's read 5 factorial. Okay, now there's a slight addition to this definition. Just there's actually a 0 factorial, and you would think, well, it doesn't even fit the definition, because normally 0 factorial, you start at 0 times and you keep decreasing until you get to 1. Well, 0 is already less than 1, so how does that work? So we basically just go by a definition of what 0 factorial is. So 0 factorial, surprisingly, or maybe not, is actually 1. You might think it should be 0, but if we apply the definition of factorial as to how we're dealing with permutations, this is kind of like saying, how many ways can we arrange 0 things? Well, there's really nothing to arrange, so I guess officially there's one way of arranging nothing. So that's why that definition's there. And we actually need that later on, because when we actually do some of these formulas later on, we will be seeing 0 factorial, so we should have a value of what that means. Okay, now there's 2 types of permutations. It's really the same thing, but it's good to separate them. The first permutation is where you have n distinct items. So for example, this would have been 5 family members. N is all, we're going to use the variable n to represent how many are we starting from, how many can we choose or pick. So how many items are we starting from? Okay, so that's n. So permutation of n items in an arrangement of all the items in a definite order. So that's kind of like what we did with the family picture. Okay, so this definition says all the items. So whatever we're starting with, that's how many we're actually arranging. Okay, so the way we can write that, okay, anytime you have permutation, you have like a capital P to tell you it's a permutation, and then the letter n is the number that you're starting from. And since this case we're actually using all of them, it's n pick n. That's how we would read this, n pick n. We can also write it to look like this, p n n. Okay, but anytime we arrange all n things from the n things we started from, There's a much easier way to write this, and it's a lot like what we did up here. We just write this as n pick n is really the same thing as n factorial. Okay, so this is where we would use n factorial right away. So that's basically what we did up here. Now, there's a second definition of permutation. Sometimes maybe if I alter this example up here, so say we had the 5 family members, but maybe we just want to pick 3 of the family members in each picture. So how many ways can we pick 3 family members in a photo? So that's what this takes into account now. So we've still got the variable n, which is what the number we're starting from. In this case, with the picture, family picture would be 5. But this time we're taking r at a time. So we're not taking all n. So this value r is always going to be, well, it could be equal to n, but it's usually going to be less than. So for our example here, we're choosing 5 family members taken 3 at a time. Okay, so how many ways could we actually take pictures of 3 family members from our family of 5? So that sounds a little more complex, and the way we would write that is instead of n pick n, it's n pick r. So for our example, it'll be 5 pick r, 5 pr. Okay, and we can also write that as pnr, whereas before we did pnn, but since those are the same 2 numbers, we decided let's just bypass that and just go directly to the n factorial. So pnr is not going to be just a straight n factorial or r factorial. It's actually something more complicated. So here's the formula. So n pick r is actually equal to n factorial over n minus r factorial. Okay, so let's just maybe for curiosity's sake, how many ways could we arrange these 5 family members? Okay, so in our case that would mean n is 5 and r is 3. So let's do an example of that here. So let's change the n to 5. 5 pick 3. Okay, so how do we calculate that? Going by the formula, n factorial, well n was 5, so it's 5 factorial on top, which is what it was when we were just looking at photos of all 5. But this time we're going to divide it by n minus r, so that's 5 minus 3 factorial. Okay, so we actually do the calculation 5 minus 3, so it's 5 factorial over 2 factorial. So if we do the math, that's 5 factorial is still the same, 120, and 2 factorial is 2. So our actual number of ways of choosing 3 of our 5 family members in a photo, we would actually have 60 ways of doing that. Okay. Now, just maybe to look at this as a slightly different way, because sometimes just blindly plugging stuff into a formula, not really understanding why it works, is not the best idea. So let's look at this from more of a perspective of what we did here. So again, if I took this time we're only putting 3 positions for our photo. Okay, instead of the 5 we had up here. So if I'm choosing, well, how many people could I put in the first spot? Well, this time I still have 5 family members I can choose for the first spot, and taking that person out, I now have 4 for the second spot, and taking that person out, I have 3 for the third spot. So again, using the product of those 3 choices, it's 5 times 4 times 3, which is equal to 60, which is the same number we got up here. So this formula actually becomes a lot more useful, especially when you're dealing with big numbers. But it's nice to see how that actually does work, because you know, we do have 5 choices for the first spot, 4 for the second, 3 for the third. Multiply those together, we get the same value. Okay. If we go look at the key concepts, this should be pretty familiar. I've got the definition for factorial. I've got the NPN, which we don't really say that often. And NPN is always n factorial. And then there's where we pick a number less than actually what are available to select. So our example here of 5 pick 3 would be an example of this. And you can see that formula that we used above here is working. So this is the key formula for today's lesson for sure. Obviously this one's important too, but this probably should be common sense at this point, but definitely something you still have to know. Okay, so let's do some examples, see if we can understand how this works. So just practicing the factorial. So 2 factorial, well, that should be pretty straightforward. That's just 2 times 1, which is equal to 2. Okay, and you can definitely try this on the you can try and make sure the factorial button works when you do 2 factorial. And then you've got 4 factorial, 4 times 3 times 2 times 1. And that works out to 24, or just do it on your calculator, 4 factorial, and then 8 factorial. I mean, I'm not going to write this one out this time, but this would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And on your calculator, you can see this is where the factorial button really helps make it a quicker calculation and avoid mistakes for missing out a number. This would be 40,320. You can see how big these numbers actually become when you have a big number to pick from. Okay, and then we have our old friend 0 factorial. Hopefully you remember what that is. How many ways can we pick 0 things from 0 things? Well, that's officially 1. And this one's interesting. This would be 70 times 69, etc., down to times 1. Well, interestingly enough, you can see how fast this function grows, the factorial function. If you try this on calculators, I believe your most calculators still give you an error. And the reason why that's an error is because the number is just too big, meaning it's like bigger than 1, I'll do scientific notation here, bigger than 1 times 10 to the 99. So that's basically a 1 followed by 99 zeros, which is a pretty big number. And most calculators can't even handle that, even with scientific notation. I'm sure there's some out there that maybe have exponents bigger than 2 digits now, but that's a huge number. Okay, so let's try working with these factorials. So, and this would be actually the formula for 10 pick 5, if you want to relate it to something. So how would we do this? Well, we could actually do 10 factorial, figure what that is, put the number on top, then do 5 factorial, figure out the number, put on the bottom, divide the 2, and you get your answer. I want to, and that's fine, doing it that way, it will work. I want to show you this in a slightly different way. So if I did, 10 factorial is 10 times 9 times 8 times 7 times 6, and then I multiply that by 5 times 4 times 3 times 2 times 1, which is really just 5 factorial. So I can just basically shorten everything else. I'll put it in brackets here. Just shorten the 5 times 4 times 3 times 2 times 1 into 5 factorial. Then on the bottom I've got 5 factorial. And these are just multiplications, just condensed multiplications. So I can actually cancel those out and then realize, well, now I can just maybe do this in my head, or a calculator. If I didn't trust my factorial button, and that's actually works out to 30,240. Okay, but you still could do this type by just doing 10 factorial, getting the number, and dividing that by whatever factorial is. It will still work. Here's where it won't work. Okay, I've got 83 factorial over 79 factorial. Now, like we said, looking back here, 70 factorial, your calculator does not like that. So either one of these, if you tried on its own, you're not going to get very far with your calculator. So we're going to do the same technique that we've done here, where you just break down the higher factorial. So 83 times 82 times 81 times 80, 3210, and then times 79 factorial, which is a long multiplication. And the reason why I did this, because we know we have 79 factorial on the bottom. So we can actually cancel those two out. And now this becomes a more reasonable math that you could actually figure out, okay? Because like we just said, you can't actually calculate these two separately and then divide. So now it's just down to multiplying these four numbers. And that is a big number still, but it's still something that your calculator can handle. 44,102,880. Okay, so make sure you understand how you can rewrite some of these factorials into something where you can cancel the big factorial and still get a calculation. Okay. All right, so let's do a couple of little word problems here. Senior choir has rehearsed 5 songs for an upcoming assembly. How many different orders can the choir perform the songs? Well, this is very similar to the question we just did with the 5 family members in the photo. We just replaced family members with songs. So this is actually, we have 5 songs to choose. So basically, n is equal to 5. Okay, and we're just arranging all of these. So this is like 5p5, which we know is just equal to 5 factorial, and 5 factorial is 120. So there's 120 different orders of the songs. Okay, so that's our first official example, other than the one I did at the very beginning. Okay, now example 4 here, indirect method. Hopefully you remember this from our last method. You're going to see how, again, that's going to be a useful method to calculate something that would otherwise seem very difficult to calculate. Okay, so this might hit home as students. How many ways could 10 questions on a test be arranged? You have the easiest question and the most difficult question, and then there's 2 options. So the first thing we're going to look at, what if we had to put the easy and the hard question together? Okay, so when you first think of this, it might seem a little tough. You might be thinking of all sorts of diagrams, but the best way I think of considering this question is if the easy and hard questions have to be together, let's kind of glue them together as one question. So now I basically got an easy hard question, and then I've got my other 9 questions. Okay, so I've got a total of 10 boxes. One box contains 2 questions. Okay, so but I'm really trying to arrange these, like I could put this EH as the second position, the last position. It doesn't matter, but I've got 9 of these. I'll just consider it sort of like 9 questions, even though it's one of those questions is a double question almost, okay? It's glued together. So the question for the first part, if they're side by side, I could actually consider them to be together. So now I've only got 9 questions. So that would actually be 9 factorial. If I'm arranging these 8 questions and the 1 double question, that would be 9 factorial ways of arranging them. But, and this is important, you could flip the order of the easy and the hard, okay? So because I can do that, I'm going to multiply this by 2. And I'll just point out why. It could be easy hard or hard easy. Okay, I didn't really quantify that when I did the 9 factorial. It was just considering that to be one question. Okay, so 9 factorial times 2, that's going to work out to 725,760 arrangements for the test. Okay, now the second part, we got the same 10 questions, an easy and a hard. This time you don't want them to be side by side. Okay, so if you go straight for the calculation for that, it can get very very complicated very fast, because they could be 1 apart, they could be 2 apart, and you start worrying about all the different situations. But the indirect method is extremely useful here, because we already know the combinations of the number of arrangements where the easy and hard are side by side. We're looking for how many ways can arrange them so they're not side by side. So what we're going to do is find all the possible arrangements and subtract the ones that are side by side, and that will give us what we're looking for. So first thing I'm going to calculate is total arrangements, and this is with the 10 questions, and they can go anywhere. Well, that's going to be 10 factorial, which is pretty big, 3,628,800. Okay, and if we want the arrangements where they're not side by side, the easy hard question, side by side, that's going to be equal to this total arrangements where there's no restrictions, 628,800, and subtract the ones where they are side by side. So I'll just show this here. So subtract that number from the big number. So that is 2,903,040 arrangements. So I hope this example really shows the power of the indirect method. It was so much easier to do than to consider all the possible cases where they're not side by side and try to figure out how many ways can we do this. So sometimes just think of the inverse, like if it's easy to calculate the opposite of what you want, that's when the indirect method is so valuable. Okay, example 5. In how many different orders can 8 nominees for the student council give their speeches at an assembly? Okay, well, hopefully this seems a lot easier than the last question, because it is. Well, you've got 8 nominees, and they each have a speech. So the number of ways of arranging is equal to, I guess we could say 8p8, because we're using all 8 speeches, and that's the same as 8 factorial, because So that is, I think we've seen this number before, 40,320 different orders. Okay, so hopefully this is quite a bit easier than the last one. It's fairly basic. Okay. All right. Example 6, student government. In how many ways could a president and a vice president be chosen from a group of 8 nominees? Now, you could do this one of 2 ways. You could use the formula. So in this case, we have a group of 8 nominees, so we know that n is equal to 8. That's how many we can pick from. But how many we're actually picking? We're actually just picking 2 positions, so that's r equals 2. So this would be so the number of ways of choosing a president, vice president would be, it's going to be 8 pick 2. Okay, and if you remember the formula for that, that is equal to n factorial, which is 8 factorial, over 8 minus 2 factorial, which is 8 factorial over 6 factorial. And if you remember how to reduce this, well, I'll do it the long way this time, but this is equal to 8 times 7 times 6 factorial over 6 factorial. So it's just equal to 8 times 7, which is 56. So there are therefore 56 ways of choosing president, vice president from those 8 people. Again, you don't have to do it this way every time. I would think more logically, at least for me, how many ways can we pick a president? Well, there's 8 people to choose from, so 8. But if we also want to choose a vice president, well, we have 7 people left to pick from because we've already picked our president. So that would be 7, so 8 times 7, which is what we ended up with anyways. Okay, so either way you want to do that question is fine with me. Okay, last example. Looks like we're going to be using the permutation formula. Okay, in a card game, each player is dealt a face-down reserve of 13 cards that can be turned up and used by used one by one during the game. How many different sequences of reserve cards could a player have? Okay, so there's a few pieces of knowledge you have to have for this course. A lot of it has to do with decks of cards. So you have to know there's 52 cards in a deck of cards. There's 4 suits, clubs, diamonds, hearts, spades. Each suit has 13 cards, and each suit has a 2 through a 9, jack, queen, king, and an ace. Okay, and we have questions regarding face cards. Well, the face cards are the jack, queen, king. So just so you know, you don't have to know it for this, but some people don't know too much about decks of cards, and sometimes we assume that everybody knows. So, so we're actually picking from our deck of cards, 52 cards. We're picking 13. How many different ways can we choose 13? How many ways can we pick 13 cards from a deck of 52? Well, that's 52 pick 13. Okay, so we do the formula. This time I'll actually do the quicker one. So the top will be the n factorial, which is 52 factorial. And the bottom will be 52 minus 13, which is 39 factorial. Okay. Now these numbers are small enough. They're still pretty big, but you could use your calculator for this. I think the highest a lot of calculators would do is 62 factorial. So this just squeaks in. If I was to do it the longer way, or I guess the longer way, but if I canceled the 39 factorial off the top, that's 52 times 51 times 50, and keep going until we get to 40. So basically 52, multiplying the numbers 52 through 40. So you could do it that way, or you could do this on the calculator and you'll get the same number. Now this is a huge number. It's actually 3.95. This is in scientific notation, times 10 to the power 21. So I don't even know what to call that number. Septillion, something like that. 3.95 septillion, possibly. So there's that many different sequences of cards. Okay, so hopefully this lesson makes some sense. It's just remember how to work with factorials. Obviously very important, using it on your calculator. The most important part is the permutations. So remember, permutations is counting the number of arrangements where the order counts. Because when we do something, we do our next type, which is combinations. Combinations is very similar to permutations, but the order doesn't matter. It's just how many ways can we pick 3 people out of a class of 31. So for permutations, the order does matter. So when you're talking about things like a photo of people, that's the way we started, or the order of a deck of cards, that's important to keep the order. Or the things like we're picking people for roles in a student government, president, vice president, treasurer. That order does matter because the positions are unique. Okay, so we got some homework questions here. Hopefully give those a try, and if you have any difficulty with them, please let's discuss that and make sure that you understand. Okay, that's it for today. We'll see you on the next lesson.